Hello everyone. Welcome to the course of deep learning with the TensorFlow. I'm happy that you follow us on these videos. So on the previous video, we saw that if we add more dense layer, or if we increase the capacity of our model with adding more hidden layers or fully connected layers, we will increase the accuracy, or we can reduce the loss or error. So as you saw, compare with the green one is just the simple softmax model, and the orange one is the fully connected layers with the 5 fully connected layers. So we saw this improvement on the accuracy and also the error reduction on the loss. So if we remove this, we see that here we have a loss function of the training. So always we have accuracy and the loss function of training, and accuracy and the loss function of the validation or test. You can see both names on literature. So we have these two, and we should also do a comparison between these two as well. So if we consider this loss function of the training and the loss function of the validation or testing, we see if we just plot these two curves on one graph, we see that for the validation loss here, we have the red one is the validation loss, and the blue one is the training loss. So we see that here at the beginning, it start from here, or the loss function start from here. So it goes slowly to down or reduced slowly. So what we can do to reduce it fastly, a little more fastly, so by changing our sigmoid activation function with ReLU, we hope to do this. So instead of having a curve like this, it will be good to have a curve like this or like this. Fastly reduction on the curve, or that it also has an effect on the accuracy. So here you see a sigmoid function at the left side, and here you can see the ReLU function. So a difference is with the ReLU function is that for the ReLU, any values less than 0 will be equal to 0, and then the value of more than 0 will assign a value. And why it's useful for us? Because biologists said that brain was working is working similar to the ReLU function compared with the sigmoid. So it was the first inspiration of using the ReLU, and also in the practice we see that it's helpful. So if we let's go back to our codes. If we see our code with the ReLU, I just should mention that you can find these codes and the text version of the website, and you can use it. You don't need to write it line by line. You can just use it and just play with this and adopt it with your problem or your data. So the same at the first block, the same at the second block. Almost all blocks are the same. I just changed a new name for this, changed it to a new name, fully connected Relu softmax. Can be any name that you like. So, and also here you can define the direction similar to the previous one, and then reshape, normalized, and convert it to the one hot encoding. Here is the only place that you need to do the modification. So instead of using softmax activation, using the sigmoid activation, we just use Relu, just this. But for the last layer, we don't touch the softmax activation. And then we create our model and we compile it, similar to the previous one, and then we fit it. So let me again to reduce it to 50, to 5, and then run it. So it goes well. So you can see even for the first epoch we have a 96%. Just by changing the activation layers, we get an improvement for our model to 96, 97. So it's I can say that we speed up our model or results. So if we back to our tensor board, and if we make our Relu softmax logs, you can see for the training, instead of starting from this point, as you can see the orange one, instead of starting at this point, it starts at this point. So it speed up our process. So although at the end it will be almost equal, but here we start at the less error. And here for the validation also, you can see here the blue one, that is the fully connected Relu softmax model. It's a start at almost the 0.15, something like this, and compare with this. And even you can see we have less loads compare on the Relu compared with the sigmoid one. And even in the accuracy, you can see, okay, we reached to the accuracy of around 98. I can say that 98.5 compared with the sigmoid one that was 0.95, 97 or 97.5% of accuracy. So an improvement, and it's enough for us. Okay. So the good reason that we use Relu, we have an improvement. That's good. So by this, if we compare it, so we can see validation loss on transparent red, and the training loss on transparent blue for the sigmoid, and for the sigmoid using the sigmoid activation function, and for in the red validation loss of the Relu function, and the training loss when we use the Relu function. You can see it's I can say that much faster, although at the end they will be almost equal. If you go more details, you see that it's not exactly equal, but it's almost close to each other. But we start from the less error or less loss. So, but if we put training loss and the validation loss, even with the ReLU, we will see there is a distance between these two. You can see here, there is a distance. So, and it's not good for our model. We call it overfitting. So, if there is the distance between them, we call it overfit. So, you see here, at the beginning, they became together till, I can say that, epoch number 5. And then as the number of epochs increased, it goes up. And for the training, the loss of the training, it goes down. So we can see this difference. So to solve this problem, one of the options that we can use is using dropout. So what we do in the dropout, if we assume such a this model, we actually turn some of the neurons off in our training model. So for example, we say that we wanted to shut our neuron down for example 50%. So 50% of the neurons in the training mood will raise, I can say, or even the weight and bias for that connection will not update. So it means that we don't use it. We don't use them on our model. But for the validation and also for the testing, we use these neurons. So here, as you see, at the left side, you can see that we have the standard neural net with all neurons that we use, and then we assign the weight and bias to them. But here, at the right side, you can see that we shut some of the neurons down, and then we use the other neurons on that. So shut on them. So this is one of the possibility to reduce the overfitting. So if we back to our model, so let me to close it. So let me shut it down. And then if we open a fully connected ReLU dropout, so here, similar to the previous one, we import our the data. This is the point that we use the dropout. As you remember on the previous videos, I said that okay, we don't use this function here on the previous codes, but here in this code we will use it, dropout. So we import the libraries. We define a new name for it, and I consider okay, I wanted to make off 25% of our neurons in our model. So just define a name, and then the same as before. You already knows what they do, and then I consider okay, keep 25%. Okay, so 25% will remain, and the rest will be off. Okay, so the same sequential dense layer, activation ReLU, and then we just add the dropout after each layer. So one dropout at the first layer, second layer, third layer, and the fourth layer. So and for the last one, we don't use any dropout. So if I run also this code and compile it, this model, and compile it, that's me again to reduce it to the 5. And if I run it, it will do this. And if we wanted to see it, we can back to the tensor board. And you see that okay, fully connected layers with the dropout. If we see with the difference with the ReLU, you can see here on validation accuracy, loose of Mac. Okay, no, excuse me. So when we keep just 25% of data of our neuron, we see that okay, we reduce the loss on the validation, and it's almost for the accuracy almost the same. For the training, it's almost the same, and also for the accuracy of training, it's again almost the same. So we reduce it. If we back to this, here we see that the transparent red we can see for the normal without dropout, and the red one is with the dropout. Okay, so we reduce this distance between the loss of validation and the loss of training. We reduced a little of this, but we still have overfitting. So what we can do to solve this problem, as we wanted to reduce the overfitting as much as we can. So here this is the question that why in general why we have overfitting. So for this, maybe we have too many neurons. So we define 200, 100, 60, and 30 at each layers. So maybe we don't have enough data. That is back to our first discussion of why we use deep learning and when we can use deep learning. Or maybe we have a bad network. So if we change our network to another model or something like this, maybe we can reduce the overfitting. So think about this. We will talk about it in the next video, and we will see how we can reduce more the distance between the loss of the validation and the loss of the training to avoid any overfitting on our model. Thank you for watching. See you on next video.